You hit send on a quick WhatsApp message, just a simple hello, and honestly it feels completely instantaneous, right? But under the surface, in literally just milliseconds, that tiny piece of data embarks on a mind-boggling journey. It gets sliced up, labeled, encrypted, converted into beams of light or electrical pulses, shot across the entire globe, and then reassembled perfectly on your friend's screen. Have you ever wondered how all of that happens without collapsing into total digital chaos?
Well, welcome to today's Explainer. I am absolutely thrilled to dive into this with you because we're demystifying the ultimate blueprint of network communication, the OSI Reference Model. Think of it as the universal translator that allows a smartphone in Tokyo to seamlessly load a web server in London without missing a beat. Here is our roadmap for today. We'll start with the network communication blueprint, then look at the software layers from application to session and the transit layers of transport and network. After that, we'll get into the hardware layers, walk through the complete end-to-end journey, and finally, compare OSI with TCP/IP. We're starting exactly where you live at the software level and digging all the way down into the physical cables.
Let's jump right into Section 1, the Network Communication Blueprint. Okay, let's talk about the number 7. The OSI model stands for Open Systems Interconnection, and it is built on exactly 7 distinct layers. Anytime a piece of data travels from one device to another, it has to pass through every single one of these layers. It was created to standardize how devices communicate, so it ensures that equipment from completely different manufacturers, like, say, a Cisco router and a Windows PC, can actually talk to each other without issues. It makes troubleshooting so much easier and basically guarantees compatibility. Now, memorizing all 7 layers in order can be a bit of a headache, so network engineers actually use a brilliant little mnemonic from top to bottom. All people seem to need data processing. That stands for application, presentation, session, transport, network, data link, and physical. Keep that phrase in your back pocket. It gives us a great mental scaffold for everything we're about to cover.
Let's start at the very top. Section 2, Software, from application to session.
At layer 7, we have the application layer. Now, the really common misconception here is that this layer is the application itself, like your Google Chrome browser or your Discord app. Actually, scratch that, it's not. Rather, it provides the network protocols that those applications use behind the scenes. When you type in a web address, layer 7 protocols like HTTP, HTTPS, or DNS are what actually format your request to go out into the network. So let's look at how these software layers actually work together to prep your data. Layer 7 handles your HTTP and DNS requests. Then it hands the data down to layer 6, the presentation layer. This is essentially your format translator. It handles data compression, formats like JPEG or UTF-8, and crucially, encryption, like SSL or TLS for secure websites. Next, layer 5, the session layer, steps in. Its whole job is opening, maintaining, and closing the communication connection. It's very much like managing a Zoom meeting from the exact moment you join until you hit leave. This analogy brilliantly illustrates how these software layers work in real life. Think of layer 7 like ordering food at a restaurant. You just ask for what you want. You literally say, "Bring me the web page." Layer 6 is like a translator making sure the kitchen understands your language, and layer 5 is like saying hello and goodbye to establish the conversation. You never actually see the kitchen, but your food arrives perfectly.
Moving down the stack, we leave the software behind and hit Section 3, Transit, Transport, and Network.
At layer 4, the transport layer, we have 2 main heavy hitters, TCP and UDP. TCP is your highly reliable workhorse. It numbers your data segments, checks for errors, and resends absolutely anything that gets lost. It's used for web browsing and emails, where accuracy is everything. UDP, on the other hand, it's built for pure speed. It doesn't check if data arrived, it just keeps firing. And that's exactly why it's used for live video streams and online gaming, where a dropped frame is vastly preferred over a delayed one. So how does TCP actually ensure this bulletproof reliability? Well, before sending a single byte of actual data, it uses a very strict 3-step handshake. First, the client sends a SYN, or synchronized request. The server replies with a SYN-ACK, basically acknowledging and accepting the connection. Finally, the client sends an ACK to confirm. Only after this polite 3-step greeting does the actual data transmission begin. Dropping down to layer 3, we hit the network layer. This is the layer that figures out how to get data between entirely different networks. If you're sending a message from your home Wi-Fi to a massive server sitting in another country, layer 3 makes that leap possible using logical addresses.
And you definitely know these. They're called IP addresses.
The core technical facts here are fascinating. The network layer turns our transport segments into packets, and the absolute superstar device of this layer is the router. Routers look at the destination IP address, whether it's an older IPv4 or a newer IPv6 address, and they calculate the best, most efficient path across the global internet to get that packet to its destination. This pathfinding process is what we call routing. The crucial takeaway is that just like a postal system or a cargo company relies on zip codes to navigate across the country, Layer 3 relies entirely on IP addresses to navigate the globe. It doesn't care about the final house yet. It just cares about getting the package to the right city.
Now we're getting into the real nuts and bolts. Section 4, Hardware, Data Link, and Physical.
To really grasp Layer 2, you have to understand the difference between an IP address and a MAC address. Your IP address is logical. It can change depending on what Wi-Fi network you join, and it's used for global routing. But your MAC address, that is physical. It is permanently burned into your device's network card at the factory, and it's strictly used for local delivery on your specific, immediate network.
So at Layer 2, the data link layer, your data is packaged into what we call frames. Devices known as switches use those MAC addresses we just talked about to send these frames locally from one specific device to another. They even check for errors along the way using a process called CRC. Finally, we hit Layer 1, the physical layer. This is the actual hardware, the copper Ethernet cables, the fiber optic glass, the Wi-Fi radio waves. Its only job is to convert your data into raw ones and zeros, bits, and blast them out as electrical, optical, or radio signals.
These analogies lock it all together perfectly. Your IP address is like the address of an apartment building. It gets the data to the right general location. The MAC address is your specific door number inside that building, so the data knows exactly which device to hit. And the physical layer, that is literally the road itself that the mail truck drives on to make the delivery.
Okay, Section 5, the end-to-end journey.
Watch how this all builds like a factory assembly line, using a concept called encapsulation. When you send an email, your data starts at the top software layers. At Layer 4, the transport layer slaps on a TCP header, turning it into a segment. Layer 3 adds an IP header, creating a packet. Layer 2 adds a MAC header and a trailer, creating a frame. Finally, Layer 1 crushes it all down into raw bits to send over the wire. It's exactly like a Russian nesting doll of data. When it reaches the destination, the whole process just reverses, unpacking the doll step by step.
In the real world, network engineers use the OSI model to troubleshoot systematically, and they usually work from the bottom up. If a user can't reach a website, you don't just guess what's wrong. You check Layer 1 first. Is the cable even plugged in? Then Layer 2. Is the switch working? Layer 3. Is your IP address correct? Layer 4. Is the firewall blocking the port? Up to Layer 7. Is the DNS server correctly resolving the website? It provides a perfect, logical checklist for fixing problems.
Finally, we reach Section 6, OSI versus TCP IP models. We've spent all this time on OSI, but we absolutely have to contrast it with the TCP IP model. When we compare the two, the OSI model has 7 highly detailed layers. It's a theoretical reference model, widely considered the ultimate educational framework for understanding networking. However, in practice, the real internet runs on the TCP IP model. It's simpler, it condenses those 7 layers down into just 4 functional layers by combining the upper software layers and the bottom hardware layers together. So while TCP IP is what we practically code and use to make the internet actually work, OSI is how we conceptualize, teach, and troubleshoot it.
Which brings us to a final, slightly wild thought. We just built an incredibly complex, 7-layer logical masterpiece of software, routing, protocols, and error checking. Yet at the very bottom, at Layer 1, it all comes down to a physical connection. If a single backhoe digging a trench accidentally cuts a fiber optic cable in the ground, that entire 7-layer stack instantly comes crashing down for millions of people. Are we over-reliant on the fragile physical threads connecting our digital world? It's definitely something to think about the next time you send a simple hello. Thanks for joining this explainer. I hope you found it as fascinating as I do, and keep exploring.